Hi everyone, I'm Munshir Jonalamwit and I'm a second year PhD student. This is our work AccuRevoke, enhancing certificate revocation with distributed cryptographic accumulators. The other authors are TJ Chang and Thang Huang. We all are from Virginia Tech. When a web browser makes a TLS request to a website, the website sends back its TLS certificate to the browser. This certificate includes the public key of the website, and the certificate is signed by a trusted authority known as CA or the certificate authority. The browser trusts the CA and knows it is talking to the real owner of the website. But what if the private key of the website is compromised due to some reasons? Then the certificate has to be revoked. So how does the revocation request work? The website asks the CA to revoke its certificate and CA does so. But how does the browser get access to this revocation information? One of the existing solutions is CRL, which stands for Certificate Revocation List. In CRL, the browser makes a CRL request and CA replies with a list of revoked certificates. But the problem is making CRL request for every TLS handshake is untenable, and also the size can be really large in practice. For example, the CRL of Apple is 76 MB. Another solution is OCSP or Online Certificate Status Protocol. In OCSP, the browser asks to the CA, "Hey, is this certificate revoked?" and CA replies with yes or no. The problem in OCSP is the CA can be overloaded by millions of OCSP requests from millions of clients, and also the privacy of the client is not preserved in OCSP. One of the recent solutions is CRL Lite. In CRL Lite, Mozilla collects all revoked and non-revoked certificates from the CA. Mozilla creates filter cascade from this list, which are cascaded Bloom filters, and pushes the filter cascade initially to the client. Mozilla also pushes the Delta update on a regular basis to the client as well. The problem in CRL Lite is that the client will rarely audit the filter cascade, which means the browser is putting some sort of trust to Mozilla, which is not desired. Also, if Mozilla wants to push the filter cascade or the Delta update to all of its clients on a regular basis, this may be very inefficient as well. Also, the client may sometimes miss the intermediate revocation between two Delta updates as well. Just to mention, CAs now rely on Content Delivery Networks or CDNs to distribute their CRLs or OCSP responses. So what are the revocation goals we want from a standard revocation strategy? So as you can see, these are the properties, those are desired from a standard revocation scheme. For example, if you look at the third property, it says the client should experience low bandwidth cost and latency. Also, if you look at the column number 7, it says there should be no overfacing by the client, which means the client should only download what it needs. But as you can see that none of the existing schemes achieves all of the goals. So here is our solution, AccuRevoke. So AccuRevoke relies on some cryptographic protocols and tools. So let's see what are the cryptographic techniques or protocols we used in AccuRevoke. So we took help of dynamic universal accumulator. And in Accumulator, there is an accumulator manager, which is like a trusted entity who chooses a secret trapdoor and creates public key from it. The good property of the accumulator is that it allows to create a concise representation of a set of elements. And we call this the value of the accumulator. And also, no matter how many elements you add into it, the size remains the same. This is like a magic. It also allows to create membership or non-membership proof, using which a member or a non-member can actually be verified. And dynamic universal accumulator also supports addition and deletion. We also took help of secure multi-party computation. So in secure multi-party computation, if we have multiple parties, where each of them have their own private input, they can actually jointly compute something without revealing their own confidential input. So now let's dive into our actual work using these cryptographic techniques. In AccuRevoke, CA works as the main source of trust like other revocation strategies. It creates an accumulator from the list of the revoked certificates. It also delegates some sort of trust to multiple third parties. So yes, you can see we have one more entity in our AccuRevoke system model, which we call edge compute providers. As I said, they are basically third-party servers who are responsible for generating membership or non-membership witnesses for revoked or non-revoked certificates for the clients. I mentioned previously that CA works as the main source of trust, and CA chooses a secret trapdoor alpha which will be used to generate the accumulator, and it creates some secret shares based on some threshold secret sharing scheme, for example Shamir secret sharing scheme, and this threshold value actually defines how many shares are required to reconstruct the actual secret. CA then sends these secret shares to all the ECPs, and ECPs will later use these shares to generate witnesses for revoked and non-revoked certificates. Also, CA is responsible for creating the accumulator from the list of the revoked certificate, and this value of the accumulator is actually public. So which means CA can disseminate this value of the accumulator to all the ECPs and the client. Now let's see how the witnesses are generated in our AccuRevoke system. So after the browser gets the certificate from a website, it requests the ECP for the witness of a particular certificate using the serial number in the certificate. The ECPs then take part in secure multiple computation and compute their share of the witness and sends the share to the client. The client can then reconstruct the actual witness from the shares, and it can verify the revocation or non-revocation status of a certificate using the reconstructed share. So if you think this is too much for the client getting all the shares by making requests, one of the ECPs can actually collect all the witness shares and reconstruct it on behalf of the client. And it can send the reconstructed witness to the client. As you can see here, client makes a request to a single ECP, for example ECP3. The ECPs can take part in secure multi-party computation to generate their shares, and finally ECP3 can reconstruct the witness after it gets all the shares from the ECPs, and it can then send the reconstructed witness to the client. And using this reconstructed witness, the client can actually verify the revocation or non-revocation status of the certificate. Also, ECPs can actually take part in secure multi-party computation and generate witnesses for revoked and non-revoked certificates for some popular domain beforehand, so that any of the ECP can actually reply instantly to the client upon request, and it can use the reconstructed witness to verify the revocation status. We say our AccuRevoke is actually very robust because if one of the edge compute providers is down, still other ECPs can take part in witness generation. So as long as we have enough number of shares from the running ECPs, client can always get the witness for a certificate. I already showed you that CS rely on CDNs to distribute CRLs or OCSP responses. But the challenge here is, for example, if the CA provides the signing capability to the CDNs, there is definitely expansion of trust to the CDNs. And the good news about the CDN is that CDNs now provide edge computing, and we call these edge compute providers in our AccuRevoke system. These ECPs actually allow us to do revocation checks very fast and near to the clients. So it will be used in AccuRevoke model for generating the witnesses very fast. Now let's dive into our experimental results. So the accumulator will be evaluated by the CA, and this is just a one-time cost. And the size of the accumulator is very small, which is 21 bytes. And I mentioned before that no matter how many elements you put into the accumulator, the size remains the same. Also, parallel processing helped us in the accumulator evaluation, as you can see it from the graph. Also, an update in the accumulator usually takes around 0.47 millisecond on average. The size of the witness for a revoked certificate is usually 21 bytes, and it takes around 0.46 millisecond on average to generate the witness for a revoked certificate. And the size for a witness for a non-revoked certificate is usually 61 bytes, and the time taken to generate the witness for a non-revoked certificate is directly proportional to the number of accumulated revoked certificates in the accumulator. So as you can see it from the graph, looks like this is a bit high cost for one non-revoked certificate. So we thought of using GPU, and just to mention that Cloudflare actually offers GPU services, and the Cloudflare can be used as edge compute providers in our AccuRevoke system. So in order to generate a witness for a non-revoked certificate on GPU, it took around 15 milliseconds. So we tried to figure out that why is it too much even if we are using the GPU. So we figured out that most of the time was actually coming from the copying, which means if we want to copy data from CPU memory to GPU memory and GPU memory to CPU memory. So we decided to do some sort of amortization, and we got a almost 8.9-fold speed up. Also, as I said, the witness can be reconstructed by one ECP or multiple ECPs or the client itself as well. And this witness reconstruction time usually depends on the threshold value which was defined by the CA in Shamir secret sharing. So at the very beginning, we tried to show that we should have this sort of properties in a standard revocation scheme. So could we actually achieve that in AccuRevoke? So we are claiming that we achieved all the properties those are desired in a standard revocation scheme. So this is a comparison of AccuRevoke with other revocation strategies. So you can see a lot of green circles here for AccuRevoke. Just to mention one, you can see if the client visit 1000 websites, the data downloaded by the client will be significantly lower compared to other revocation strategies. And the delay is not that bad as well. This is very similar to OCSP. So we decided to simulate the behavior of a client, and results shows that if client visits 1000 domains, the data downloaded by client will be the lowest compared to the other revocation strategies. So AccuRevoke is the clear winner here. Also, in terms of delay experienced by the client, the AccuRevoke performs well. Though it is slightly higher than the SierraLite because SierraLite has local revocation checking, but given the advantages AccuRevoke has, we can say that AccuRevoke is a very good choice to use as a revocation strategy. So thank you everyone for watching. If you have any questions, just shoot me an email to munshira@vt.edu. Also, our source code is available in GitHub in the given link. Thank you.